So we're looking at the domain of a function. That function has a variable and a denominator. I can set the denominator equal to 0. That is a troublesome spot. I don't want to be dividing by 0. And so that tells me, in this case, that x equals 3 is a troublesome spot. So my domain, and this is where you have to be real careful, is all real numbers except 3. Or you can say all real numbers except when x is equal to 3. And there's a lot of different phrasings, but it's everything except 3. Okay. And we saw last time that these types of situations give us that asymptote. Right? That's what we saw at the very, very end of last class. Okay. Well, the other type of function that we're going to be concerned about with domains is a function which has some sort of a root, whether it's a square root, cube root, fourth root, whatever. Let's just start with the square root. Let me do a different one. Let's do x plus 6 underneath a square root. Well, if we have square roots around and we want to graph on the Cartesian coordinate plane, the Cartesian coordinate plane only allows for real numbers in our x's, real numbers in our y's. And therefore, we get a bad spots or bad spots when we get square root of a negative. Square root of a negative number is not going to be real. You don't get a real number. And so we can't graph that on the Cartesian coordinate plane. Now, there's a couple of different ways to view this. I can view this on saying, well, I want, therefore, the thing underneath the root to be positive. Or I could say, I should say above 0 or above, not necessarily positive. 0 is okay. It's okay to do the square root of 0. Or I could say, well, the bad spots happen when the thing under the square root is negative. It doesn't matter which way you do it. So you can do it saying, well, here's all the bad spots, or here's all the acceptable spots. I'm going to do it in this case with the acceptable spots. So we want whatever is under that square root to be 0 or above. Subtracting 6 from both sides doesn't change the order of the sign. And so what that tells us is that we want all of our inputs to be at least -6. -6 or higher. And so that's our domain. Our domain is all real numbers which are bigger than or equal to -6. Hello.
Hello. Second.
I think when I do the drop down menu, like when you have to pick the domain, you can just pick this. You can just pick the algebraic version of doing that. Okay. Does that work? So if we're looking for the domain of something with a square root, that bad spots happen when we get square roots of a negative number. Therefore, we want anything under the square root to be at least 0. And this would go for all even roots. So if I did a 4th root, really nothing changes. Or if I did a 6th root, or an 8th root, or a 10th root, all even roots have that issue. That underneath, we want to have positive values underneath. Because when you have an even root, whether it's a square root, a 4th root, 10th root, you need to input 0 or above underneath there. Now that is different if I had a cube root. If I have, let's say, a function h of x as a cube root of x minus 10, it is okay to have negative numbers underneath of a cube root. And if I know that, then I can say, well, if it's okay to have negative numbers, it's okay to have positive as well. Then there's really no issues here. Anything I plug in is going to be acceptable. So the domain there is all real numbers. Or let me just shorthand it so I don't have to write as much. Remember that symbol stands for all real numbers. So square roots, I want to avoid negatives under. Cube roots, not that big of a deal to have negatives under there. Okay. And obviously things can get more and more and more complicated. For instance, let's do the domain. F of x is equal to, let's do 4 times the square root of x minus 7 divided by x squared plus 2x minus 24. Oh, you know what? I screwed that up. I want to do x minus 1. I wrote the thing down. My apologies. Here there's multiple places for bad spots, right? Our denominator could be 0. And then we have a square root, and we want to avoid square roots with square root of a negative number. So a lot of things to avoid. Avoid denominator of 0. You don't want to divide by 0. And we want square root, or we want to, let's say, avoid square root of negative. I'll write it that way. X squared plus 2x minus 24 is my denominator. I want to avoid when that is 0. Now, we're gonna, later on, we'll look at how to solve this in general. But for right now, if I give you a quadratic set equal to 0, the way to solve this, I'll give you one that can be factored. Does that make sense? So remember how to do that. Factors of negative 24 that add to 2 are 6 and negative 4. You guys remember doing that back in the day, hopefully? You look at factors of negative 24, like negative 1 and 24, negative 2 and 12, negative 3 and 8, negative 4 and 6. And you say, which ones of those add to a positive 2? This one. Now I knew it was going to add to a positive number, so I always wrote the bigger one with the positive. But you could also list the others, like if you did a positive 1 and a negative 24, that's fine, or a positive 2 and a negative 12. But they have to multiply to give you 24. Multiply to give you negative 24, and then add to give you 2. And then we say, well, that means either x plus 6 is 0, or x minus 4 is 0. If I subtract 6 from both sides. And then I add 4 to both sides over here. I end up getting 2 spots that I want to avoid. I want to avoid negative 6, and I also want to avoid 4. All right, because both of those are going to lead to a denominator of 0. So that is one troublesome spot. My other troublesome spot will happen if I do a square root of a negative. So that means I want to have the thing underneath the square root to be at least 0. When I avoid a negative underneath the square root, I need to have thing underneath the square root to be 0 or positive. 0 or above. adding 1 to both sides means that I want all of my x's to be 1 or more. So if you're thinking about the domain here is all x, all values that are 1 or more, but then I have to avoid these. Technically, the -6 is less than 1, so I don't even have to worry about it, but you have to be 1 or more and avoid 4. Okay, being 1 or more already avoids the -6. That makes sense? So my domain is the values or the real numbers which are above 1, okay, except when x is equal to 4. And I could say and when x is equal to -6, but the -6 is already taken care of by that. So I don't have to rewrite except also -6, because that's already taken care of. Okay. And you can see the messier and messier looking functions may have, or they could have, in theory, really crazy domains. All right? Really crazy looking domains, like in this one. We have some denominators. We have essentially 2 places we have to avoid for our denominator to be non-zero. And then we have sections where I get a square root or negative there. So I want to avoid that as well. If you wanted to graph that on Desmos, you could. It'd be really ugly looking. Questions about domains? Yeah.
Do we just ignore the 4 on the outside of that square root then?
Yeah, so this 4 really doesn't impact because 4 times anything is whatever it is, right? You can multiply any real number by 4. So the square root of the negative, we only really care what happens underneath the square root. So if this were, let's say, square root of x minus 1, times 5 out there, and then plus 8x minus 2 up there. Really, the only troublesome spot would happen with the square root of the x minus 1. All right. So you can do lots and lots of other things on the outside of that square root, adding terms, multiplying by constants on the outside. And really, the only troublesome spot is when the inside underneath the square root is negative. So yeah, you can kind of ignore all this other stuff and just focus on inside underneath the square root. All right. Now, I want to do a couple of things based on some graphs. All right. This one I usually have set up. It's been a weird morning with all the snow and delay. So we're going to take a look at Desmos for just a moment. And we're gonna take a look at the domain and range of graphs using decimals, all right, or using just, I should say, a graph of various functions. So if I say, well, don't worry about what I'm typing here. All right. It's like, all right. All right, so let's say you didn't see me type in what I just typed in. But I gave you this section of a graph that looks like this. All right. This graph in red. So if you see a section or a function graph like this, and we have to recognize the domain and the range. Well, the domain is the x values, the input values, which this graph can take on. Now, I purposefully started and stopped the graph at specific points. All right. Let me do that. You'll notice that the leftmost point is the point -1, 4. However, there's an open circle at that point. That means my graph doesn't touch that point. On the right-hand side, the rightmost point is 3, 0. And it is a closed circle. A closed circle indicates that my graph touches that point. All right. So if I'm thinking about the domain, I'm going from the smallest x value to the largest x value. So the x values go from -1, but remember we don't touch -1, up to an x value of 3. So the domain goes from -1 up to 3. And because we don't touch -1, there's different notations. I'm going to use inequality notations when I write this. So the domain is all numbers that are bigger than -1, but notice I cannot equal -1. And that are under 3. But remember, I can touch 3. That's the inequality notation for the domain. All x values between -1 and 3, where you can't touch 1, -1, but you can touch 3. There's also an interval notation that says we're going from -1 to 3, and the way you indicate you can touch one of those numbers is that if you can touch the number, if your graph touches the number, you put a square bracket on that 3. And if you cannot touch a number, you put a parentheses. So this is also a different notation, meaning the same thing. It's all numbers between -1 and 3, where you cannot touch -1, but you can touch 3. So again, that's just interval notation.
Do we need a graph calculator?
What's
Do
that?
we need a graph calculator? Is this the right one? Is there?
You can have that one.
Oh,
Yeah,
okay.
that's
Can I
fine.
use the other one too?
What's that?
Can I use the other calculator too?
Yeah, you can use a graphic as well. Yeah. Now, as far as the range goes, range is a little bit trickier. Range is where your Y values or your output values are between. So I look at the topmost point. The topmost point still -1, 4. So that's the highest Y value is a 4. Right? Highest Y value is a 4. Now I can't touch 4, but I can get as close as I want to it. That's what that open circle there means. Now, be careful because the bottom value is not 0 for Y's. The bottom value is actually -2.25. Might be a little bit hard to see there, but I'm just highlighting it. If this were on a, it's probably gonna be a better example on the homework, where you can clearly see 0.25 or something. But the bottom Y value regardless is -2.25. And so if we're talking about the range, we say the bottom value is -2.25, the bottom Y value. You can actually touch that point, or my graph touches that point. So Y is greater than or equal to -2.25. And the Y value goes all the way up to 4. But I can't touch 4. That makes sense. So with inequalities, it would be this. Y value is between -2.25 and +4. I cannot equal +4, but I can equal -2.25. And if I were doing this in interval notation, I always go from my lowest value, comma, my highest value. And then because my graph touches -2.25 as a Y value, I put a square bracket on that side. And I put a parentheses with the 4 because my graph does not touch the value of 4. All right. Interval notation has those square brackets and parentheses when you can touch and when you cannot touch. So most of that is just being able to read off and understand what the Cartesian, what the graphed version on the Cartesian coordinate plane looks like. Okay. And if you can read that off, we'll be in good shape. Okay. Now, one other thing, so we've dealt with domain and range. We'll deal with some of the other scenarios as well as we keep moving on. Yeah, we got time. Remember some of the other things I said, we're gonna look at domain, range, talk about x-intercepts, y-intercepts, intervals for increasing, decreasing, constants, points of discontinuity, f of x for specific values of x, all that kind of stuff. Well, we can do that, a lot of those things. On graphs like this as well. All right. So let's begin talking about what it means to be an increasing or decreasing. Now, when you look at a graph, when we say increasing or decreasing, we mean as you look at this from left to right. If you were on this graph moving from left to right, what would the point be doing? Well, notice on this section between -1, let me give a step so we can see more here. All right. So from -1, x value of -1, all the way down to the x value of about 1.5. As you move to the right, your point is going down. So we're decreasing. So we're decreasing in this section, right? Now, once you hit 1.5, your graph changes. And now moving left to right, the point is going up. So we're increasing. So if I said between -1 and 0, is the graph increasing, decreasing, or constant? You'd say, well, between x values of -1 and 0, that's where we're going down, so we're decreasing. If I said, well, between 2 and 3, what's happening? Well, between x value of 2 and x value of 3, we're increasing. That's not very shocking, is it? Hopefully. Now, here's where sometimes people get thrown off. Let's say we go from 0, 0 to 3, 0. If I said between those 2 points, what's the graph doing? The graph is not staying constant. Just because I started and ended at the same y value, 0 in this case, does not mean that the graph is constant. As you can see, for part of the way, it decreased, and the other part an increase. So between 0 and 3, well, it's neither decreasing nor increasing. It's kind of doing both, right? For part of the way it's increasing, for part of the way it's decreasing. So don't think just because you started and stop at the same point, that means it's constant. It's not constant. A constant graph is one that looks like no. Like that. Right? That's a constant graph. This purple one. It stays steady the whole time at y value of 3. Okay.
So no matter what the number is, it stays the same.
Yeah, so no matter what the x value is, the y value stays the same. Now, there is like a formal definition of increasing and a formal definition of decreasing, where it says I'll write this down, but I'm not going to spend a lot of time on it. A function f of x is decreasing. Now let's do increasing. That'll be easier. Increasing on an interval, we'll say from A to B. That means from x value of A to x value of B. And if for every, let's say, x value that is bigger than A, for every 2 x values that are distinct between A and B, we have, so what we're saying is that this is the smaller one. This is the one, the x1 is our first x value, it's more to the left. Our x2 is the one that's more to the right. So if the x1 is more to the left, we get some point. Increasing, we want our x2, which is more to the right, to go up, right? Does that make sense? Now, what's the y value? It's whatever you get out when you plug in x1 into your function. What's the y value over here? It's whatever you get out when you plug in x2 into your function. So what's this need to be? The f of x1 needs to be smaller than the f of x2. So the output value, when you put in the lower one, needs to be lower than the output value of the higher one. Okay. So that's sort of the formal definition of increasing. It's a lot easier to see visually than sometimes the formal definition almost gets in the way. And then decreasing, it looks the exact same, but now we have to have the output value low. If we had constant, then all of the output values would be equal. All right. So decreasing on interval means for all we have that way. So it's going down. The one that's further to the right has lower y value. So we're moving down. And then constant on the interval means for all we have equal. So all of the output values are equal. That's one way to define it. On the constant, that's not the only way to define it, but that's one way to define it. Now, what am I gonna do? I'm gonna say we should understand what increasing, decreasing, constant is just by looking at the graph. Okay, so if you look at the graph or a section of the graph, and I say, well, between x values of 1 and 0, or I misspoke, between 0 and 1, let's go smaller to lower, smaller to higher. What's the graph doing? Or between x values of 3 and 4, what's the graph doing? Is it increasing, decreasing, constant? You can look it up, look at the graph and understand decreasing, increasing, constant. Pretty straightforward. So let's move on to the last thing in 1.2 that you'll need, and that's the concept of piecewise defined functions. All right. Probably you've heard of these before. Piecewise defined functions are functions that have multiple components. Or pieces. And so the output values are going to be defined by what the input values are. And we're going to have different formulas for output values depending on what the input values are. So we have different formulas, expressions to find output values depending on what input value we plug in. I would say depending on the input value, should probably say the input value. Right, way to put it. Okay. So for example, I'm sure a lot of you, you've seen these things before, but let's define a function this way. Usually the notation is like a set bracket. And we'll have 3x minus 4. And that's the formula I use, that's the expression I use to find the output value for all of the x values, which are less than 2. Negative x squared plus 2. I'll use that expression for all of the x values that are between 2 and 3. And then I will use x minus 10 for all of the x values that are greater than or equal to 3. So we have 3 different expressions to give me my output values, depending on where the input value is that I plug in. So if I were to plug in, for instance, a -1, the first thing I do is I go to my over here when it says what input values. And I say -1 is less than 2. So I need to use this expression, this 3x minus 4. So f of -1 is equal to -7. So your input of -1 gives an output of -7. I said, what's the output if our input is +1? Well, if my input is +1, +1 is still less than 2. So I'm still dealing with this expression, 3x minus 4. So if my input is a +1, looks like my output is a -1. Based on that calculation. If my input is 2, you have to be pretty careful. Because while this says for all x less than 2, use the first expression, less than 2 is not the same thing as 2. This says all x which is greater than or equal to 2. Because this one has the equality in it, I have to use this expression, x squared plus 2. Negative x squared plus 2, sorry. So for 2, when I input a 2, I use this expression. If I would have input a 2.5, I would have also used this expression because 2.5 is between 2 and 3. If I input 2.75, I'd also use this expression because 2.75 is between 2 and 3, so on and so forth. Once I get to 3, this one does not have the equality, this one has the equality. So if I get to 3, I have to plug in 3 into the x minus 10 expression. If I want to plug in the number 5, 5 is greater than or equal to 3. So I'm going to plug it into that third expression. And so you can see kind of how this operates. Plug in 12. 12 is more than 3. So I plug it into that third expression. Right. Again, many of you, I'm sure, have seen piecewise defined functions before. In terms of dealing with plugging them in. The plugging in is usually fairly straightforward. You just have to be really careful with the 2 and the 3, because sometimes, obviously, if the equal sign were up here, for the 3, you'd be using this expression, if the equal sign were up there. And the equal sign will not be on both in general, all right? So it won't be on both in general. Because that would force this. Let's just say, for instance, if I had an equal sign here and here, if I plugged in 2, I'd get 1 point on this one. I plugged in 2, I'd get a different point on this one. That would fail the vertical line test, so that wouldn't be a function anymore, right? So in general, we'll only have equality on one of those and inequality on the other. Any questions about plugging in and getting out outputs for piecewise defined functions? Now, I want to look at what the graph of this piecewise defined function would look like. It's going to take me a minute to plug it into Desmos. I'll show you how I do this, but it's not that important that you know how to do this. All right. So we want our function to be 3x, there's probably a different way to do this. 3x minus 4 for x values less than 2. So you just, in set brackets, just say for x values less than 2. You want your function to be negative x squared plus 2. For x values between less than or equal, excuse me, less than or equal. So between 2 and 3. Again, just use set brackets there. And then we want our output to be defined by x minus 10 for x bigger than or equal to 3. So, oops. There you go. Now I like to make them all the same color, just do this. Now here's one of the drawbacks of graphing this way. On Desmos, if you scroll in, you can't really tell if this touches 2 or doesn't. But see that visually. So oftentimes I'll add a point. You see that is the point 2, negative 2. That came from 3x minus 4. Does it touch or not? Well, if we do not have equal to, it's not going to touch. So oftentimes you'll see a point and that point will be an open circle to indicate it doesn't touch there. All right. By the way, the point, this other one, 2, negative 2, it does touch. So oftentimes you'll see a closed point to indicate that it does touch. Here's an interesting little tidbit. Notice that between the second piece of our function, this piece here, and the third piece of our function, they actually kind of converge to the same point. See that? 3, negative 7. So this piecewise defined function looks like that, graphically. Now this was a pretty difficult way to graph a piecewise. I graphed basically all 3 pieces separately and then added on the points at the end. But you can see this piece, and this piece. You can see the 3 kind of separate pieces. And piece number 2 and piece number 3 actually kind of at x value of 3 are going to the same point. And this graph sort of shows the idea of discontinuity versus continuity. All right. This is a very common phenomenon in piecewise defined functions, to have a point of discontinuity. So let me talk about continuity in general. There's a fancy math definition using limits for what is continuous. For this class, we don't need that fancy definition. All we're going to say is that a graph or a section of a graph is continuous if I can draw it without having to lift up a pencil. You okay with that? So for instance, this graph between value of 7 and value of 10, so x value between 7 and 10, that's continuous in that section because I can draw it without having to lift up a pencil. That makes sense? However, if you look between 1 and let's say 2.5, once I get to 2, to get to the other side, I'm gonna have to lift up my pencil. Right? So we have a point of discontinuity, or this graph is not continuous at x value of 2. All right, because there's a gap in our graph right there. So because of that gap in our graph, our graph is not continuous at x value of 2. However, as you can see here, if you're graphing through 3 to the point with an x value of 3, you can graph this without lifting up your pencil. So this graph is continuous at x value of 3, but it is not continuous at x value of 2. Does that make sense? So that's the concept of what a continuous function is. And a lot of times when you have piecewise defined functions, you have these places where it's not continuous. The other place where we saw it wasn't continuous, when we had these troublesome spots like zeros in our denominator. If I have f of x equals, let's say, let's do 1/2 x divided by x minus 2. You'll notice at 2, I'd have to take my pencil. Let's say if I'm going left to right, it would go down all the way as far as I can draw, and then I have to lift it up and start over here. So at that asymptote, it's not continuous either. So this one is also not continuous at the x value of 2. We have that value that's discontinuous. All right, any questions about that? Ideas about discontinuity? Any of those things? Don't think there's anything to add there. Okay. So piecewise defined functions. Looking at the domain and range. figuring out, again, I messed with a little bit points of discontinuity. Increasing, decreasing, that's more 1.3. We'll get into that very quickly here, but hopefully this is fairly straightforward. By the way, this doesn't always have to have 3 sections. It can have 2 sections, or it can have 4 sections or 4 pieces for your outputs, whatever number you want. You can have, again, 2, 3, 4, however many expressions you want for your outputs, that's fine. Okay, all of those are piecewise defined functions. All right, since we're about out of time, I think I will stop there with stuff. We'll get into a lot of 1.3 and 1.4 next class period. Because of Martin Luther King Jr. Day, we don't have class on Monday, this coming Monday. But we will have class on Wednesday, all right? And we should be able to cover all of 1.3, 1.5 next Wednesday. All right, other than that, I will see you next time.